All right, physics reaction video number 28. I'm going to try with the lights in the background. Eventually I'll get a lamp. I don't know, maybe this is better for my lighting. It looks like this is a lecture. Just the way these things are labeled, I think they might be like a lecture posted for the students. Not sure. It's quite long. We won't we won't do all of this, obviously.
Okay, so last time we talked about the concept of momentum, which involves the multiplication of a mass times its constant velocity. Mass times velocity is momentum, or you say constant momentum because it's a constant speed.
So he said he started out with last time, which is awesome, right? To sort of build that bridge from the old material that you've seen. What's not clear to me is how much of this was written last time. It's not clear whether he's going to be writing live or if he sort of pre-writes his stuff. So I'm curious about that.
So P equals MV. The units are kilogram meters per second.
Or palms.
And we know that an outside force is going to be responsible for changing the velocity of an object. So that's what we know in Newton's second law, that it's going to take an outside net force to accelerate the object from one speed to the other speed, to another speed. That's the initial speed could be 0 to some non-zero speed, or it can come from a non-zero speed all the way down to 0. So in either case,
sounds like
that
1D.
is under the influence of an outside force. So momentum is kind of like an extension, if you will, to Newton's first law. One second. So it's kind of like another way of looking at an application of Newton's first law,
Yeah,
where the net force in the system will be equal to 0. And when there is a net force, we change the object's velocity. Therefore, we will be changing the object's momentum as a result, because we know momentum is mv. And so when we have an outside force to cause an acceleration, we are going to change the object's momentum. And we also understand that in order to change the object's velocity, that is, change the object's momentum, it's going to take a certain amount of time to do so.
Oh, I like that.
There's a rate of change of things, a rate of change of position, giving velocity. Rate of change of velocity is an acceleration.
I really like that, right? Because if you have an abrupt change of your velocity or an abrupt change of your momentum, I guess that's technically an infinite force right there, right? Because it's like these jolt, these impulses, these abrupt changes are an infinite force. And so usually we use forces that aren't abrupt so that we can really think about what happens over time. Many of you know that I really championed the momentum first approach that a few different books use. You heard me joke earlier about the units of momentum being the palm, because we use it so much we should have a name for the unit. And to me, when I think about Newton's 3 laws, there we go. So a lot of people start here and go down to the bottom, but I really think of these 3 laws in a slightly different way. I say that, look, objects exchange momentum. That's just the way the world works. Objects exchange momentum. So that's actually Newton's 3rd law, right? You give me some, then you gained, I lose, right? So objects are constantly exchanging momentum. And sometimes it's fast and sometimes it's slow. And so the rate that you exchange momentum with other people, these little, I don't know, particles of momentum or something, the rate that you change is a useful thing to know. So let's just give it a name. That's how, you know, palms per second is our rate. And let's give it a name. I don't know. How about force, right? And so particles exchange momentum. They do it at some rate, so we keep track. And then, I mean, I guess if you don't exchange any momentum, then you just, you stay where you are. Boom, there's Newton's first law, right? So I tend to go bottom up when thinking about those laws. What I really like about what he's doing here is he had some stuff from before, and he's really driving home. Look, if you have a change, then this changes. If there's no force, then this is just going to sit still, boring. And then he's really trying to hit the timepiece. That's what he started out most recently. I'll just back up a little bit. I'm not sure if that worked. See if it did. If it did. Okay.
So delta V over delta T is acceleration. So mass times acceleration is a change in momentum over change in time, which is a force. So in order to change an object's momentum, which takes time to do so, which is this first expression here on the left, that is, you're actually looking at another equation for force, for an outside net force, equals mass times delta V over delta T, which is acceleration. So this is another way of expressing Newton's second law. F net is mass times acceleration, or in terms of momentum, the outside force here changes the momentum.
Yeah, I love how he's really driving it home.
Can't change anything without a time interval, as with an appreciable time interval. That is one that is measurable. And then the next part here, we were trying to get an equation for
sounds like maybe still review.
Momentum. We multiply both sides by delta T, and we get rid of the delta T here, and then we just basically come up with an equation that verifies our intuition that delta P, change in momentum, is mass times delta V. Because P equals mv, then change in momentum or change in P is mass times.
So I talked about this in yesterday's reaction, or day before or something, this notion of pulling the M out and really living our lives with this idea that the mass stays the same eventually gets us in trouble, right? Eventually when you're doing the rocket equation, you're like, oh, what? Mass change? Oh, shoot, if the mass, oh man, this is hard. But as usual, I really sort of love how these teachers are embracing the early scaffolding. Like, look, come on, this is pretty straightforward stuff. If, two balls hit each other, or, let's roll a ball down a ramp or something. We're not talking about the thing melting. And so it's just fascinating to sort of watch, to see that happen, and to think about the changes you'd have to do when you shift over to the rocket equation. I also want to say, by the way, that over here, these are pretty artistic. So it looks like he uses a vertical scroller. I don't know what software this is. Can't quite see. And it's a vertical scroller, so he doesn't really use left-right very much. He just kind of keeps writing down, down, down. But look how pretty these are. Pretty interesting. Also notice the dates here. Some really interesting things. I actually think this is from this year. So let me look at the calendar here. So November 12th, was a Thursday, and November 16th was a Monday. So this was a weekend here. And then look, so I don't know whether this is high school, college, I'm not sure. Although I did a search for AP, so probably high school. So it's sort of interesting, right? Maybe some block scheduling or something. And look that today he's going to have a couple of days worth of notes. So a lot going on. It's hard to see exactly. There might be the slightest hint of a red box right there. So we might be in the middle of the day, and he might still be contemplating review here. It's also interesting, right? So this is in the future. So is he going way back, and then is he going to come forward to today? So I'm a little bit confused about that. I think I might go just a little bit longer here because I also want to hear what he's doing for new content. So I might fast forward in a second.
Times delta V. These are vectors. You don't have to write the arrow, but it's all things are written for a reason to let you know. Oh, okay, those are vectors, and my mass I know is a scalar. It doesn't have any direction, just a magnitude. And delta V is final minus initial. Delta anything is final minus initial. Delta X, X final minus X initial.
Love that.
Delta V, V final minus V initial, and so on. And delta P, P final minus P initial.
It's so interesting to really indoctrinate our students into the way that we use symbols, right? So a lot of symbols represent a physical quantity you can go measure in the real world. And then we have sort of decorations, right? So we've got We've got vector symbols that are decorations. And it turns out that the delta is a decoration. You say, oh, wait, there's a delta on both sides. I'm going to cancel it. We don't do that. And so it's really fascinating to hear him say, hey, well, when we say delta, we always mean final minus initial. And so, there's no perfect way to represent all of this stuff. And this is the way most of the textbooks that we use have decided to do it. But to really try to get the students to understand that this is like a unified new thing, this whole thing, the parameter, its name, the fact that it's a vector, and the fact that we're contemplating its change, that this whole thing is something we're going to deal with, as opposed to saying, oh, cancel my deltas. And of course, if a student were to do that, right, well, if delta P equals M delta V, then I'm going to cancel my deltas. Oh, and then P equals MV, and I've heard that before, so I'm pretty sure that's true. So watch out, right? The canceling of deltas might look algebraically or mathematically correct, but it's not what we're trying to say. All right, so I'm actually just going to go forward here. Just to see, I'm not sure. Let me just skip ahead here.
Okay, so so we're going from an initial velocity to some final velocity by way of a force in a certain amount of time. We then took a look at impulse. Impulse is the application of a force in a certain amount.
So it could be that this is just a review. I'm just going to see if I can drag this. I don't understand what this little blue box is here. It's kind of weird. So can I drag him? I can go back. I can go forward, but there's some reason I can't go. I'm just going to pause my video, see if I can figure that out. Okay, so I jumped ahead. Still not sure why it's not letting me do my normal jumps, but whatever. To a point where it looks like he's starting a new problem. So I really liked the early scaffolding he was doing, but I also wanted to see how he was doing a new problem. I think this means he's doing problem 9.1. Let's listen. Oh, maybe it's a new section. Cool. Oh, cool.
Okay, so we're from last time, section 9.1. We've just been talking about how impulse is the change of momentum.
So now we can understand a little bit better what he's up to, right? So you can see that he's actually way up here on November 19th, I guess. So what is that? 5 days later from the stuff that he was reviewing. So I think that a lot of that, so what do we have? About 15 minutes of review, really trying to build it up. And now it's like, okay, let's jump into this new stuff. What's a little bit confusing to me is why this would be in a new chapter. Oh, maybe it's, okay, conservation of momentum, because I'm just interpreting 9.1 to be maybe like a chapter or section number. So maybe all the previous stuff was maybe chapter 8. And so now he's like, okay, oh boy, we had to really understand all that stuff. And I know I walked you through it and we worked on some problems, but I just wanted to hit the highlights. And after 15 minutes, he's like, okay, we're finally ready. Here we go. And, let's be honest, that is so useful, right? To really remind the students what they've been doing and to get the vocabulary back in their brains. So if this is the 19th, it's a week after that original one. But I think it's the next day, because I think there was 16, 18, and now the 19th. So I don't know what kind of school this is, but now we're finally into some new stuff. And now, of course, the big difference between having things already pre-written and then writing it out. One of the things that I'll talk about with teachers a lot is this idea of leaving time for students to take notes, right? So one way to do that is to write it yourself, right? So if you have the time to write it, they have the time to write it. But there's also this interplay, right? Like, well, we want their brains turned on, and maybe I just want to give them what's written or give them a handout so that they can see. And so there's just this really fantastic mix of different approaches. He's writing and talking at the same time and, doing a pretty good job, I think, of saying, okay, well, here's what we're up to. Let's get going.
Because it takes a force, coupled with time, force in time, to change magnitude
I like that.
and or direction.
Yeah, it's important. Cool. And again, staying with constant mass,
so
but
again,
good enough.
Just repeating what we've been talking about, just as the intro and what we were talking about last time. Just to write up the full equations, impulse is force delta t, which is changing the object's momentum, which is mass times change in velocity, which we know that delta v is v final minus v initial. So all of those things are equivalent.
I like that.
Those are all impulses. We don't change the velocity, that is the momentum of an object, without the application of an outside force. So again, let's consider a ball hitting a wall. So we have the ball coming in, certain mass.
These problems are tough. These problems are super tough. And the reason they're tough is because the force is really hard to explain. Frankly, even the conservation of momentum is hard to explain. If this wall tends to be infinite mass, these are tough problems, right? Because it kind of depends what you're really trying to drive home. Now, he wants to look at how the velocity changes. And he's like, oh, well, this thing changed velocity, so it must have received an impulse. And he's going to say, my guess is he's going to say, well, what happened to that conservation momentum? Well, it was this external force. And so if the particle received an external force, so it's momentum change. So I think these infinite wall problems are tricky depending on what the student's thinking about. Also, I finally realized, duh, this is the volume, not the fast forward thing. So whatever, we're doing fine. It's a Thursday, give me a break.
Mass and going to the right, so that's going to be a positive velocity. And then there's an impact of the ball on wall and wall on ball. The force of impact here is going to be the impulse provided by the wall on the ball, and that impulse is going to be the force of the ball on ball times delta t. The ball is going to rebound, and so
this idea of using vertical space on a diagram to represent time is a great use of space. It allows you to really circle things and address things that matter at different moments in time. But it is tricky, right? Because this looked to be a physical drawing of a wall, and I think it is playing that role. And then we're saying, well, it comes in, and then it hits, and then it leaves, right? This idea that you're using vertical space in the diagram to represent basically different moments of time, I think it's tricky. But again, and I've said it so many times, video can really help, because as you're explaining and you're moving on, I don't think the students are going to get lost here. And they're probably going to not even realize how useful it is that he's given some space to be able to say the various things that he's talking about.
So we have the same ball, and now that's the final case.
Ooh, that's tricky. That's tricky. I wonder if he meant that. I wonder if this is going to trip him up. Right, because, I mean, these are vectors, then you wouldn't need this negative sign. If these are speeds as represented in the right direction, like rightward, then you would need this negative sign. I'm curious if he's going to get some extra negative signs.
So we have interaction of ball on wall, impact of the wall on the ball, and then it goes back the other direction. So that's our final case where the momentum is actually changing.
So here he means other direction.
In magnitude, but definitely by direction. So the wall has provided an impulse. All right. Now let's say
I like that extend page.
We have two balls that are moving towards each other. Okay, so we have this, let's say we have ball number one, let's call it mass one, and it has an initial velocity going to the right. And then we have ball two, and since it's going to the left, it's going to have...
Wow, okay. That's tricky. So he's putting in the negative signs because he really wants them to understand right versus left. And the thing is, the students get it. They understand what's happening. But what happens when they start plugging things in is they can really have some additional negative signs. So I do wonder how he will tend to do that. I'm not sure if there's some examples in here. Maybe I'll fast forward to see. The other thing I wanted to say is that these collision problems are so interesting because in the student's experience, it's not going to stay in one direction, right? So they ricochet off some crazy direction. But almost always we want them to consider, no, assume that doesn't happen. And so I actually think that doing things that are sort of constrained in one dimension, like on tracks or something, which is quite often what they might be doing in lab, can really help it constrain the one-dimensionality of it. But it's interesting that their first experience, like playing pool or billiards or something, is that this almost never happens. So I want to fast forward to see how he solves a problem. Okay, so it looks like they might start about here. Let's just jump to that. Nope, I want to go back up just a little bit. Okay, so let's see what happens here with the negative signs.
Delta V2. And we know that those deltas are final minus initial.
Okay, so what he's saying here is that this is Newton's third law here, equal and opposite. So that's why this negative side is going to come down here. So there's an additional negative sign. So far we have two negative signs in the problem.
Okay. So after the impact, object one rebounds. It goes, let's say it goes back to the left, M1, and then we say negative V1 final. And then object number two.
Being very consistent, negative means left.
M2. V2 final.
Move my,
so what I'm going to do now is I'm going to take this equation and develop a relationship between their momenta. And then we'll see what we can say at the end about that relationship. So the first side of this equation, we have M1 delta V1 is going to be V final 1 minus V1 initial. And that's going to be equal to negative M2 V2 final minus V2 initial, because that's their equal and opposite impulses. The impulse of 1 on 2 is equal to 2 on 1, and that's also equal to the F delta T is equal to M delta.
So, okay, so if we're following along, this negative sign is coming along for the ride. These negative signs have to do with the definition of delta. These negative signs, this one and the similar one for the other one, hasn't really shown up yet.
The V1 equals the opposite of M2 delta V2. And this is the same equation stretched out in terms of their final and initial velocities. So simplifying that, so we have M1 V1 final, just switching the subscripts around. M1 V1 initial equals negative M2 V2 final, and then we add those. This here is going to be M2.
Okay, so we can see where he's going. He's going to land at conservation of momentum. Let's just get there a little bit further. Yep. So he lands at conservation of momentum. Okay, so it was really, really intriguing. Like, he never had any numbers to plug in. He was just going for this, right? He was going for this, and he gets there. But it's really, really intriguing that the negative sign that he uses to indicate leftward travel doesn't really show up in here. And so I think that the students really need to think about how does this work when they're plugging numbers in. So it's a really fascinating interplay, right? We only have so many symbols. Does he really want to write out moving to the left, or just stick a little negative sign saying, I mean that it's traveling that way now, or that way? He did have some arrows drawn, right? But I think that the students are going to have to practice this. And then, of course, this conservation of momentum, it's a vector thing, right, is another way to do it. Well, I'll just write the initial stuff and then I'll write the final stuff and set it equal to each other. So really, really intriguing how he did that. And so I think I'll probably stop right here. The things that I liked about this were the review, for sure. The review was super awesome. Making sure that the vocabulary was there. I think that explaining the connection between impulse and conservation of momentum is really, really interesting. Though the wall problem, right? If they go back and say, what happened to that momentum? Oh, the wall absorbed it, right? We know that stuff's going to happen eventually. And so I think that this work here has really set up some really dynamic conversations that the students can have with this teacher. So very, very cool. All right, everybody, have a great Thursday. Sorry, I screwed up so many things. And well, this experiment with the light I think was medium. I hope you have a great day. And remember, physics teachers are awesome.